Hello students, welcome to this video on a new topic, thermal properties of matter. This is given in chapter number 11 of physics for class 11. In first part, we will study about the temperature and heat, measurement of temperature, ideal gas equation and absolute temperature, as well as thermal expansion. Please listen to my lecture carefully with full attention and note down all the important points. Wherever you feel that I am going fast, please pause the video and listen once again. This is a very interesting topic. We have all a sense of heat and temperature. Temperature is a measure of hotness of a body. A kettle with boiling water is hotter than a box containing ice. In physics, we need to define the notion of heat, temperature, etc. more carefully. In this chapter, you will learn what heat is and how it is measured, and study the various processes by which heat flows from one body to another. Along the way, you will find out why blacksmiths heat the iron ring before fitting on the rim of a wooden wheel of a horse cart, and why the wind at the beach often reverses direction after the sun goes down. You will also learn what happens when water boils or freezes, and its temperature does not change during these processes, even though a great deal of heat is flowing into or out of it. Let us start. Temperature and heat. Temperature is a relative measure or indication of hotness or coldness. Heat is a form of energy transferred between two or more systems or a system and its surroundings by virtue of temperature difference. Temperature is a relative measure or an indication of hotness or coldness. A hot utensil is said to have a high temperature and ice cube to have a low temperature. An object that has a higher temperature than another object is said to be hotter. Hot and cold are relative terms like tall and short. We can perceive temperature by touch. However, this temperature sense is somewhat unreliable and its range is too limited to be useful for scientific purposes. Generally, heat transfer takes place between the system and the surrounding medium. That is, when the temperature of the body and its surrounding medium are different, until the body and the surrounding medium are at the same temperature. That means heat transfer takes place from one body to another body till equilibrium is achieved. The SI unit of heat energy transferred is expressed in joule and represented by a symbol capital J. The SI unit of temperature is Kelvin. Please note the difference. The SI unit of heat energy is in joules and the SI unit of temperature is Kelvin, and it is also sometimes expressed in degrees Celsius is a commonly used. Degree Celsius is the commonly used unit of temperature. When an object is heated, many changes may take place. Its temperature may rise, it may expand or change the state. Change the state means it may become from solid, that is ice block, to liquid, or liquid to gaseous state or steam. Measurement of temperature. A measure of temperature is obtained using a thermometer. Many physical properties of materials change sufficiently with temperature. Some such properties are used as the basis for constructing thermometers. The commonly used property is the variation of volume of a liquid with temperature. For example, in common liquid in glass thermometers, mercury or alcohol, etc., are used whose volume varies linearly with temperature over a wide range. So, to summarize, temperature is measured using a thermometer. The volume of a liquid like mercury or alcohol varies with temperature. Hence, these are used in constructing a liquid in glass type of thermometer. Thermometers are calibrated so that a numerical value may be assigned to a given temperature in appropriate scale. For defining any standard scale, two fixed reference points are needed. The ice point and the steam point of water are two convenient fixed points and are known as the freezing and boiling points respectively. These 2 points are the temperatures at which pure water freezes and boils under standard pressure. The two familiar temperature scales are Fahrenheit temperature scale and Celsius temperature scale. The ice and steam point have values of 32 degrees Fahrenheit and 212 degrees Fahrenheit respectively on the Fahrenheit scale, and 0 degrees centigrade and 100 degrees centigrade on the Celsius scale. On Fahrenheit scale, there are 180 equal intervals between two reference points, and on the Celsius scale, there are 100 points. These values are shown in the plot of Fahrenheit temperature, that is TF, versus Celsius temperature TC, as shown in the figure on the right hand side. The x-axis is temperature in degree centigrade and y-axis is temperature in degree Fahrenheit. Please observe here carefully the temperature scale, that is in Celsius scale there are 100 equal differences between 0 and 100 degrees, whereas in Fahrenheit scale they have values 32 on the Fahrenheit scale, 32 and 212. Please note here it is 32 and upper side is 212, and this is TF scale. And there are between 32 and 212, there are 180 equal intervals. These are shown on the right hand side, that is y coordinate, and on the x coordinate there are 100 points. A relationship of converting two scales may be obtained from the graph shown on the right hand side, that is Fahrenheit scale TF versus Celsius scale TC. In a straight line, this is a straight line as shown in the figure, whose equation is, the equation of straight line is TF minus 32 divided by 180. There are 180 parts, hence it is TF minus 32 over 180 equals TC divided by 100. This is how we can obtain the relationship between the two scales. IDL gas equation. Liquid in glass thermometers show different readings for temperatures other than the fixed points because of the differing expansion properties. That means the liquid used has different expansion properties, hence the temperature readings are different for readings other than the two fixed points. That is, two fixed points are the freezing point of ice and the boiling point of water. Other than that, they show different readings, which is due to the different properties, expansion properties of the liquid used. Whereas a thermometer that uses a gas gives the same readings regardless of which gas is used. We may use different types of gases, but still the readings will be same. Experiments show that all gases at low densities exhibit the same expansion behavior. The variables that describe the behavior of a given quantity, that is say mass of a gas, are pressure, volume and temperature. That's represented by capital P. That is, pressure is capital P, volume is capital V, and temperature is capital T. That means the variables that describe the behavior of a given quantity of gas are pressure, volume and temperature. Here capital T equals T plus 273.15, where it is the temperature. Small t is the temperature in degrees centigrade. Capital T is the absolute temperature that you are going to study in the next slides. Hence, capital T is equal to small t plus 273.15. Now, we will analyze Boyle's law, which is used for framing of ideal gas equation. Boyle's law states that when temperature is held constant, the pressure and volume of a quantity of gas are related as PV is equal to constant. That is, capital P is the pressure and capital V is the volume. The product of pressure and volume equals constant, provided the temperature is held constant, keeping the temperature constant. This relationship is known as Boyle's law, named after Robert Boyle, who lived from 1627 to 1691. Robert Boyle is the English chemist who discovered this equation. Another law is Charles' law, which states that when the pressure is held constant, the volume of a quantity of gas is related to temperature by the relationship capital V by capital T is equal to constant. That is, the ratio of volume to temperature is constant. This relationship is known as Charles' law, named after French scientist Jacques Charles, who lived from 1747 to 1823. Low density gases obey these laws, which may be combined into a single relationship. That is, the Boyle's law and Charles' law can be combined in case of low density gases which obey these laws. Therefore, the ideal gas is PV by T is equal to constant. That is, the product of P into V divided by capital T is constant, because PV is equal to constant by Boyle's law and V by T is equal to constant by Charles' law. Hence, PV, combining both these two, we get PV by T is equal to constant. This relationship, that is PV by T is equal to constant, is known as ideal gas law. In general, ideal gas law equation is written as PV is equal to mu into capital R into capital T, where P is the pressure, V is the volume, that is equal to mu is the number of moles in the sample of gas, and capital R is called the universal gas constant, and T is the temperature. R is called the universal gas constant, that is R is equal to 8.31 joules per mole per Kelvin. So you remember the value of universal gas constant, and the ideal gas equation is given by the relation PV is equal to mu into R into T. Mu into R is constant. Absolute temperature. In the equation for ideal gas, we have seen in the previous slide the relationship PV is equal to mu into RT. Here, the mu is the number of moles in the sample. Mu is the number of moles in the sample of a gas, and R is the universal gas constant. Whereas P is pressure, V is the volume, and T is the temperature. Since mu and R are constant, and if we keep volume constant, P is directly proportional to the temperature. This relationship allows a gas to be used used to measure temperature in a constant volume gas thermometer. So the thermometer using the gas is a constant volume gas thermometer. Holding the volume of a gas constant, it gives P, the pressure, is directly proportional to T, that is temperature. Thus, with a constant volume gas thermometer, temperature is read in terms of pressure. The figure 1 on the screen shows a plot of pressure versus temperature. Temperature is on the x-axis and pressure is plotted on the y-axis. This is in respect of low density gas kept at a constant volume. Thus, a plot of pressure versus temperature gives a straight line. This is a straight line as shown in figure 1. However, measurements on real gases deviate from the values predicted by the ideal gas law at low temperature, but at the relationship is linear over a large temperature range. That is, say range is from here 200 minus 200 to 100 degrees and above, and it looks as though the pressure might reach zero with decreasing temperature if the gas is continued to be a gas. That is, at minus severely low temperature the state of gas may change. The absolute minimum temperature for an ideal gas, therefore, is inferred by extrapolating the straight line to the axis, as shown in figure 2. This temperature is found to be minus 273.15 degrees. So, if you extrapolate these straight lines and allow it to meet on the x-axis, it meets at the point minus 273.15 degrees and is taken to be 0 point. So here you see minus 273.15 degrees Celsius is taken as 0 Kelvin and that is 0 Kelvin as shown in figure 2. The same scales are also plotted in the figure 3, that is comparison of Kelvin, Celsius and Fahrenheit temperature scales. This is a Fahrenheit temperature scale and this is a Celsius scale and this is a Kelvin scale. So the stream point is in Kelvin scale it is 373.15 Kelvin, which corresponds to 100 degrees centigrade in Celsius scale, that is equal to 212 degrees Fahrenheit, whereas the ice point on Kelvin scale is 273.15 Kelvin and the Celsius scale is 0 degrees Celsius and in Fahrenheit scale it is 32 degrees F. So the 0 of Kelvin is equal to minus 273 degrees Celsius and minus 450.69 degrees Fahrenheit. The size of unit in Kelvin and Celsius temperature scale is the same. So the temperature on these scales are related by the equation capital T is equal to Tc small t suffix subscript c plus 273.15. Let it be equation 2. Thermal expansion. It is observed that sometimes sealed bottles with metallic lids are so tightly screwed that one has to put the lid in hot water for some time to open it. This would allow the metallic lid to expand, thereby loosening it to unscrew easily. Similarly, in case of liquids, the mercury in a thermometer rises when the thermometer is put in slightly warm water. If we take out the thermometer from the warm water, the level of mercury falls again. In the case of gases, a balloon partially inflated in cool room may expand to full size when placed in warm water. On the other hand, a fully inflated balloon when immersed in cold water would start shrinking due to contraction of air inside. Thus, Most such substances expand on heating and contract on cooling. A change in temperature of a body causes change in dimensions. This increase in dimension of a body due to increase in temperature is called thermal expansion. I will read this sentence once again. The increase in dimensions of a body due to increase in its temperature is called the thermal expansion. The expansion in length is called linear expansion. The expansion in area is called area expansion, whereas the expansion in volume is called volume expansion. All the three expansion, that is linear expansion, area expansion and volume expansion, are shown in figure 1. This is in length, expansion in length, hence it is linear expansion. This is two-dimensional expansion and it is area expansion. It is expansion in all the three directions. It is called volume expansion. If the substance is in the form of a long rod, then for a small change in temperature delta T, the fractional change delta L over L is directly proportional to delta T, where delta L is the change in length and L is the original length. And this ratio delta L by L is proportional to change in temperature delta T. So removing the proportionality constant, we get delta L by L is equal to alpha 1 into delta T. Let it be equation 1. Here alpha 1 is called coefficient of linear expansion or linear expansivity and is the characteristics of the material of the rod. Similarly, in case of volume expansion, the fractional change in volume, that is delta V by V, where delta V is the change in volume or delta V is the volume of a substances for change in temperature, that is delta T, and define the coefficient of volume expansion or volume expansivity. It is given as alpha V, alpha subscript V is equal to delta V by V into 1 over delta T. Let it be equation 2. In the equation 2, alpha V is called the characteristics of the substance, but it is not strictly a constant. That is, alpha V is strictly not a constant. It depends in general on temperature. See, the graph in figure 2 shows the variation of the constant, so-called constant alpha V with respect to temperature. As the temperature is on x-axis and alpha V y-axis. If you see here in the curve, almost at the higher temperature, it is constant. Thus, it is seen that alpha V becomes constant only at a high temperature, that is this flat curve. Coefficient of linear expansion and coefficient of volume expansion. Table 1 shows the average values of coefficient of linear expansion for some of the material which are taken in the temperature range of 0 degree centigrade to 100 degree centigrade. From this table, if we compare the value of alpha 1 for glass and copper, we find that copper expands about 5 times more than the glass. See the figure here, copper is 1.7 into 10 to the power of minus 5 per degree Kelvin, whereas glass is 0.32. Almost it is 5 times. Normally, metals expand more and have a high values of alpha 1. Please see the figure, the table here. The first column shows the material. This is aluminum is a metal, brass is a metal, iron is a metal, copper is a metal, silver is a metal, and gold is a metal. Whereas glass is not a metal. Its value is low. Alpha 1 for metals is higher, whereas for glass it is low. Glass and lead it is low. Then the next table, table 2, shows the average value of coefficient of volume expansion for some of the common substances in the temperature range 0 degrees centigrade to 100 degrees centigrade. We can observe that the thermal expansion of these substances, solids as well as liquids, is rather small. With material like Pyrex glass, Invar, that is a special type of iron nickel alloy having particular values, low values of alpha V. From this table, we can find that the value of alpha V for alcohol, ethanol, the last row, is more than the value of alpha V for mercury for the same rise in temperature. The different values are given and some of them are metals, the others are non-metals. Please compare the values which of alpha V which is given per degree Kelvin. Water exhibits an anomalous behavior. It contracts on heating between 0 degrees centigrade and 4 degrees centigrade. The volume of a given amount of water decreases as it is cooled from room temperature until its temperature reaches 4 degrees centigrade. Please see the figure above. As we heat from 0 degrees to 4 degrees centigrade, its volume decreases. See here, the volume decreases until its temperature reaches 4 degrees centigrade. Below 4 degrees centigrade, the volume increases. Here below 4 degrees, to the left hand side of this point, the volume increases and therefore the density decreases. The density here decreases. You see in figure 2. This means that water has maximum density or 4 degrees centigrade. You see here. The density increases and then above 4 degrees the density decreases. This property has an important environmental effect. Bodies of water such as lakes, ponds, which freeze at the top surface. You must observe in the lakes and ponds, the top surface of the water freezes first. As the lake cools towards 4 degrees centigrade, water near the surface loses energy to the atmosphere, becomes denser and sinks. The warmer, the less dense water near the bottom rises. However, once the cold water on the top reaches temperature below 4 degrees, it becomes less dense and remains at the surface where it freezes. If water did not have this property, lakes and ponds would freeze from bottom up, which would destroy the much of their animals and plant life. So this particular anomalous behavior is very helpful in environmental protection. Thermal expansion of gases. It is observed that sometimes sealed bottles with metallic lids are so tightly screwed that one has to put the lid in hot water for some time to open it. This would allow the metallic lid to expand, thereby loosening it to unscrew it easily. Similarly, in the case of liquids, it is observed that mercury in a thermometer rises when the thermometer is put in slightly warm water. If we take out the thermometer from the warm water, the level of mercury falls again. Similarly, in case of gases, a balloon partially inflated in a cool room may expand to full size when placed in warm water. On the other hand, a fully inflated balloon, when immersed in cold water, would start shrinking due to contraction of the air inside. It is our common experience that most substances expand on heating and contract on cooling. Gases at ordinary temperature expand more than the solids and liquids. For liquids, the coefficient of volume expansion is relatively independent of temperature. However, for gases, it is independent of temperature. For an ideal gas, the coefficient of volume expansion at constant pressure is found from the ideal gas equation, that is PV is equal to mu into R into T, where P is the pressure, V is the volume, mu is the moles, number of moles, and R is an universal gas constant, and T is temperature in absolute temperature, that is Kelvin. Let it be equation 1. At constant pressure, that is at P is constant, the equation can be written as capital P into delta V. Delta V is the change in volume equals mu R constant as it is, and change in temperature is delta T. That is, for a change in delta T, the volume changes by delta V. Let it be equation 2. So dividing equation 2 by equation 1, we get delta V by V equals mu r gets cancelled, delta T by capital T. Or we can write it as transferring delta T to the denominator on the left hand side. We can write is delta V by V into 1 over delta T is equal to 1 over T. So this relationship delta V by V into 1 over delta T is the coefficient of volume expansion represented by symbol alpha V. That is equal to right hand side is 1 by T. So this is the equation for coefficient of volume expansion for an ideal gas. Let it be equation number 3. At 0 degree centigrade, alpha V, the value of numerical value of alpha V equals 3.7 into 10 to the power of minus 3 per Kelvin, which is much larger than the solids volume alpha V for solids and liquids. So equation 3 also shows that alpha V is inversely proportional to the temperature. That is, if we increase the temperature, the value, numerical value of alpha V decreases. For a gas at room temperature, the constant pressure, that is at room temperature and constant pressure, alpha T is 3300 into 10 to the power of minus 6 per Kelvin. This value is for at room temperature, alpha V at room temperature, whereas at 0 degree centigrade it is 3.7 into 10 to the power of minus 3 per Kelvin. Please note the difference between the two due to the variation in temperature. This is as much as the order of magnitude larger than the coefficient of volume of expansion of typical liquids. Now we will derive an equation for relation between alpha V and alpha L, that is coefficient of volume expansion alpha V and coefficient of linear expansion alpha L. Consider a cube of length L that expands equally in all directions, that is length into breadth into height. So volume has three dimensions, that is length into breadth into height, when its temperature increases by delta T. So we know that by definition alpha L is equal to delta L by L, that is change in length to original length divided by 1 over delta T divided by delta T is alpha L. This is the basic definition of coefficient of linear expansion. Now if we take the volume, volume is given by if there is a change in length in all the three directions, then length increases in all the three directions, that is L plus delta L and into whole cube. L plus delta L whole cube minus original length is L cube. Therefore, change in volume is L plus delta L whole cube minus L cube. So, using the formula a cube minus b cube and expanding and neglecting the smaller terms, we get delta V is approximately equal to, almost equal to 3L square into delta L, where delta V is the change in volume equals 3L square. L square is the original length into delta L, change in the length. That let it be equation 1. Here we have neglected delta L because delta L is much smaller than the length L. Neglect the smaller terms delta L square and delta L cube. Multiply and divide the right hand side by L. So this right hand side of equation 1 by L we are multiplying. Therefore right hand side becomes 3L square into L is L cube. 3L cube divided by L into delta L. So that becomes L cube is volume V into delta L by L. So delta V is equal to 3V into delta L by L. So R we can write delta V, that is on the left hand side, divided by V is equal to, retain these 3 as it is, into delta L by L. Now again divide the left hand side and right hand side by delta T to get the definition of alpha V and alpha L. So when we divide delta V by dt, delta T, we get delta V by V into delta T is equal to 3 into delta L by L into delta T, which is written and shown on the screen. Let it be equation 2. Therefore, the delta V by V into delta T is nothing but coefficient of volume expansion. So, we can write the left hand side as alpha V, that is equal to 3 times delta L by L into delta T is alpha L. So, let it be equation 3. So, alpha V, that is coefficient of volume expansion, is equal to 3 times the coefficient of volume coefficient of linear expansion. Alpha V is equal to 3 into alpha L. Similarly, we can obtain the relationship between the area coefficient of area expansion alpha A equals 2 into alpha L. Let it be equation 4. Hence, this is the relation between alpha V and alpha L. Please write step by step and you follow it. Pause it wherever you feel that I am going fast. Next we will take up term thermal stress. Thermal stress is the stress produced by any change in the temperature of the material. It is induced when the temperature is raised or lowered and the body is not allowed to expand or contract. It includes both heat and cold. That means when a metallic rod is heated and it is not allowed to expand, so then the temperature rises, and due to increase in temperature it produces a thermal stress. Similarly, if you reduce the temperature, then also thermal stress is produced. So it is produced when the body is not allowed to expand or contract. So I will define thermal stress once again. Thermal stress is the stress produced by any change in temperature of the material. It is induced when the temperature is raised or increased or lower and the body is not allowed to expand or contract. Includes both heat and cold stress. Example. Consider a steel rail of length 5 meters and area of cross section 40 centimeters square that is prevented from expanding. That means it is not allowed to expand while the temperature is raised by 10 degrees centigrade. So temperature increases 10 degrees centigrade and its area of cross section is 40 centimeters square and length is 5 meters. The coefficient of linear expansion alpha L of steel is 1.2 into 10 to the power of minus 5 per Kelvin. This is from the tables we had shown in the previous slides. Thus, the compressive strain is delta L by L equals alpha 1 for steel into delta T. That is the definition, delta L by L into delta T. Delta T we have taken on the right hand side. Therefore, delta L by L is equal to alpha 1 of steel into delta T. That is equal to alpha 1. The value of alpha 1 is 1.2 into 10 to the power of minus 5 and delta T he has given us 10 degrees centigrade. So it is 10. So the value is now becomes 1.2 into 10 to the power of minus 4. Young's modulus of steel we know also from standard table. Y steel is equal to 2 into 10 to the power of 11 newtons per meter square. Therefore, the thermal stress developed is delta F by A equals Y, that is Young's modulus of steel into delta L by L. This is the 2.4 into 10 to the power of 7 newtons per meter square. Which corresponds to an external force of delta F is equal to A into Y steel into delta L by L is equal to 2.4 into 10 to the power of 7 into 40 into 10 to the power of minus 4. That is equal to 10 to the power of 5 newtons. If two such rails are fixed at the outer ends or in contact at the inner ends, the force of this magnitude can easily bend the rails. This is an example. Next, we will take up some worked examples. Question 1. Show that the coefficient of area expansion, that is delta A by A into 1 over delta T of a rectangular sheet of solid is twice its linear expansivity. In the previous example, that is in slide number 10, we have proved that delta V by V into 1 over delta T equals 3 times alpha 1. So in this example, you have to prove we have to prove for coefficient of area expansion alpha A is equal to 2 times alpha L. Consider a rectangular sheet of solid material of length A and breadth B as shown in the figure on the right hand side. So here it is the length A, length of the rod is A and breadth is B. This is the A, B. Original width and original length is here, this part, lower part. So now when it is heated, when the temperature is increased by delta T, its dimensions change. So it increases by delta A. So area is increased by delta A and breadth is increased by delta B. That is equal to alpha 1 into B, and delta A is equal to alpha 1 A into delta T. From the figure, increase in area is equal to delta A1, that is delta A1 is this upper part plus delta A2, this is delta A2 and delta A. So this is the expanded portion, increase in the area. Therefore, adding A into delta B plus B into delta A, this is B into delta A plus delta A into delta B. These are the things. Please understand the figure. Draw it very neatly and clearly, and you will write the labeling. If you do properly, you will understand everything. So, the increase in area delta A is equal to A into delta B plus B into delta A plus delta A into delta B as shown in the figure on the right hand side. Therefore, it can be written as A into alpha 1 B into delta T plus B into alpha 1 into alpha L into A into delta T plus alpha 1 whole square into AB into delta T whole square. Therefore, that is equal to alpha 1 AB delta T into 2, adding 2 plus alpha 1 into delta T plus equals alpha 1 into A, capital A into delta T into 2 plus alpha 1 into delta T. Since alpha 1 is equal to 10 to the power of minus 5 per Kelvin from table 1, the product of alpha 1 delta T for fractional temperature is small in comparison with 2 and may be neglected. That means this can be neglected. This term can be neglected. Hence, delta A by A is into 1 by delta T is equal to 2 times alpha 1. Hence, alpha A is equal to 2 times alpha 1. Sometimes we can refer it as alpha 1 for linear expansion or alpha L as the case may be. Now we'll take up question number 2. A blacksmith fixes iron ring on the rim of a wooden wheel of a horse cart. The diameter of the rim and the iron ring are 5.243 and 5.231 meters respectively at 27 degrees centigrade. To what temperature the ring be heated so as to fit the rim of the wheel? Please read the question again and we will solve it. Answer. Given T1 is equal to 27 degrees centigrade and L length of T1 is equal to 5.231 meters and LT2 is equal to 5.243 meters. So, LT2 is equal to LT1 into 1 plus alpha 1 into T2 minus T1. Substituting in the formula, LT2 is 5.243 equals 5.231 meters plus 1 plus alpha 1 is 1.20 into 10 to the power of minus 5. This is from the tables for steel, wooden wheel and steel ring or iron ring per Kelvin into T2 minus 27 degrees centigrade. So we have to find the temperature T2. Solving it, we get T2 is equal to 218 degrees centigrade. So the ring should be heated to 218 degrees centigrade to fit the rim on the wheel. This we come to the end of part 1 of thermal properties of matter. In the next lecture, we will take up specific heat capacity, calorimeter and other sections. Please practice it and listen and practice. Till then, goodbye.